Hello guys, Mr. G here. Today we're going to be practicing what we learned about work. So we're going to be practicing the definition of work, calculating the network, as well as calculating using the work energy theorem. We're going to be solving three questions. The first question said a block of 85 kilograms start moving from rest, and let's get this and write some data already here. It means the initial velocity starting from rest, the initial speed of the object is 0. Under the action of a force of magnitude 240 Newton, this is the applied force, 240 Newton, that forms an angle of 20 degrees with the horizontal, that is the angle of inclination. The coefficient of kinetic friction is 0,2, so this is kinetic coefficient of friction is 0,2, no unit. The block move a distance of 8 meters, and this one will be the displacement there. So here we have all the data, and I don't think is a need for us to isolate the data because we have more or less everything marked here. We have, if you want, you can now isolate all the data together. Question 1.1, calculate the work done by the pulling force. And just to keep the same steps we always follow, before we even start answering the question, we're going to do the free body diagram. And because we've done it so many times, I'm not going to be repeating the steps of doing the free body diagram. I'm just going to show you the answer. And guys, this is the free body diagram. We have all the forces acting on this object. So question 1.1, which is quite simple, calculate the work done by the pulling force is the work done by the applied force. In other words, this is equal to applied force multiplied by the displacement multiplied by the cosine of theta. Remember, theta in this case is the angle of inclination, which is going to be the angle here. This is going to be in the dative, you can see there is 20 degrees. So when you substitute, the answer is going to be 1804,21 joules. This is the first answer for the first question here. Very simple. Question 1.2, calculate the work done by the kinetic frictional force. Now, to calculate the work done by the kinetic frictional force, obvious is going to be question 1.2, work done by friction is equal to frictional force multiplied by displacement multiplied by the cosine of theta. Now, let's find theta for the frictional force. So for the frictional force, the theta is going to be the angle from here all the way there, and that one is 180 degrees, guys. It's quite simple there. But now the problem is not that one is quite simple. The problem is we don't have friction, okay? And then we have to go all the way back using Newton's law to calculate friction. All right, now, how do we calculate frictional force? Frictional force is equal to the kinetic coefficient of friction multiplied by the normal force. And now here, we still having problem because we do not have the normal. And how do we calculate the normal? We go to Newton first law. In the y-axis, because the normal force is in the y-axis. So saying that, we come here and we say F net is equal to 0. We are working in the y-axis. I want you to note that one. So if we go back to the free body diagram we have here, there is a thing. We have a force which have an angle with the horizontal, and the force is not in any of the axes. So we must get the component of that force. So this force must go projected to the x, and you will have the applied force in x, which is not needed at the moment, and is going to be to the y, and is going to get here the applied force in the y y-axis. Okay, and this one was done before. I will leave the link of a question like this one that you can go back and recall what you are going to see for Newton's law. So in the y-axis, we are on this side here. Okay, so if we move here back to the actual calculation of the normal, you have that normal plus the applied force in y minus weight is equal to 0. I will leave the link so you can watch this one at the video on how to calculate this normal, but this is how it is done. So normal is equal to weight minus applied force in the y-axis. And if you substitute all here, which we are going to do because the purpose is not Newton's law, is m multiplied by g minus applied force in the y-axis is the opposite side to the angle, as you can see there. So it's going to be equal to applied force multiplied by sin theta. Okay, and then when you substitute all the values, which is the leftovers here, it's going to be normal force will be 750,92 Newton. And now this one, this value here from the normal force must go and be substituted there for the frictional force, which we were going to substitute real fast. So now we are back here, frictional force. Then frictional force is going to be equal to 150,184 Newton. So with the normal force, now we may calculate the work done by the friction force. So we substitute everything here by work. And the answer is negative 1201,472 Newton. This is the answer for the second question, or question 1.2 here. Next question. The next question said calculate the net work done on the block by all the forces. Now, the work done by the block by all the forces, in this case we don't include the components, we include the blue force, the ones I marked first, which are the actual forces. Remember, the components are not forces, that is the breaking up of a force. So to calculate this one is question 1.3. Net work, remember, is the algebraically addition of the work done by all the forces. So will be the addition of work done by the applied force plus the work done by the normal force plus the work done by the frictional force plus the work done by the weight. Those are the forces acting there, guys. However, you know that the angle between the normal and the angle between the weight with the displacement is 90 degrees. So the work done by the normal force in this case is 0, as well as the work done by the weight. So in other words, it's only the work done by the applied force and the work done by the frictional force. So when you substitute here for the net work, you will get then the final answer for the net work is 602,738 joules. That is the final answer for net work. Okay, so now we're going to the next part of this question. The question is quite good. Using the work energy theorem, the speed of the block when it has traveled in 8 meters. So calculate the speed of the block when the block has traveled 8 meters. So let's go to the next page for this one. Now here we're looking for the final speed of the block, and we have to use the work energy theorem. So the work energy theorem is net work equal to the change in kinetic energy. Therefore you must start from there so you can get 1 mark, because that is the starting point. The net work we already calculated, and then the change in kinetic energy is final kinetic energy which is half mass final speed square minus initial kinetic energy, which is half mass initial speed square. So if you substitute, however, remember the object starts from rest, so the initial speed is going to be 0, and that is all 0. So when you substitute the values here, we get that the final answer is 3,777 meters per second. This is the speed, no direction needed, and this is the final answer for question 1.4. We go to question 1.5. Apply Newton's second law of motion to calculate the magnitude of the acceleration of the block. So now it's question 1.5, which they're asking you to use Newton's second law to calculate the acceleration of the block. So how to calculate the Newton's second law? I'm going to try to leave links also for this question because it's not related and you may forget. The net force is equal to the product of mass and acceleration, that is Newton's second law. And we're going to go to the x-axis. Now for Newton's second law in the x-axis, what forces do you have there in the x-axis? You have the applied force in x and you have the frictional force. Those are the two forces you have in the x-axis. And therefore you are coming here and you say applied force in the x-axis minus frictional force is equal to the product of mass and acceleration, and the rest of this one is substitute. However, you don't have this value here, but remember it's the adjacent side, so this one is equal to applied force multiplied by cosine of 20 degrees, because that is the inclination of the force, or the angle of the force. Frictional force, which we did calculate previously, multiplied by mass and acceleration. And when you substitute all this one, final answer here is going to be 0.89 meters per second square. Now, in the direction of motion, they ask you to calculate the acceleration. So, in the positive direction, that is all I'm going to write for the acceleration here. And this is the very first question we're going to do. It's quite long because it's a lot of questions related to the same thing, but it's a very good question. So we're going to activity 2, or question 2. A crate of mass 30 kilograms. This is the mass of the crate. This is the mass of the crate. M equal to 30 kg. It's placed at the point A on a rough inclined plane. So there is friction. The plane is rough. That makes an angle of 25 degrees with the horizontal. You can see the angle in the picture. The crate slides down from rest, so the initial speed of the crate here is equal to 0 and travels a distance d, that is the displacement, for it reaches the bottom point B with a speed of 2 meters per second. The speed here, final speed there, is equal to 2 meters per second. Is an important data there. The crate experiences a constant frictional force of 100 Newton. They are giving you the friction, so this case you don't have to calculate friction while sliding down. Draw the free body diagram to show all the forces acting on the block while it moves from the position A to B. Now for this free body diagram, they ask in question 2.1, you are not going to draw the axis. They only want the forces, okay? But before doing that, we are going to draw one with the axis. All right, so the one with the axis, remember I said you are going to have the x-axis that's going to correspond to the surface, and this is a more or less corresponding with the surface, and with the x is the displacement. That one is for the purpose of the angles later on, but the rest of the thing is exactly the same. So what forces are acting on this object as it's sliding down? Here we have first of all the friction, which is in the opposite direction of motion. This is frictional force. You have normal force because it's on a surface and the surface is experiencing a force perpendicular to it, which is the normal force, and the other force is weight down here. This one is the third force. There's only three forces there, which is here. So now, saying that, all you have to do is transfer this one without the access to this question. And that is not that bad. It will be quite simple. This is the object. Frictional force is going to be pointing in this direction. It's in opposite direction of motion. Perpendicular to frictional force. Make sure this force is perpendicular. This is the normal force. What I mean is make sure this angle here is 90 degrees. This 90 is not part of the free body diagram, and then the weight pointing down, and this is the free body diagram they're asking you to do in question 2.1. Question 2.2 state the work energy theorem in words. Work energy theorem in words. And this theorem states that the net work done on an object is equal to the change in the object's kinetic energy. You have to do it in words, but the symbol is here. We just use it in the previous question. Is equal to the change in kinetic energy. It's going to be given in the exams, in the formulas. Please go and use it. Question 2.3. Use this work energy theorem to find the distance the ray travels from A to B. And now for this question, which is 2.3, we have to start with the work energy theorem before anything else. Net work is equal to change in kinetic energy, and then further on, if you want, you can break this one into part. Net work, what forces are acting here? Work done by frictional force plus the work done by the normal force, which is also going to be zero in this case, plus the work done by weight, and everything is going to be equal to a half mass final speed square minus half mass initial speed square. Now, what I recommend you here is to calculate individually the work done by each of the forces, and we are going to quickly do that. So let's begin by the work done by frictional force here. So the work done by frictional force is equal to frictional force multiplied by the displacement multiplied by the cosine of 180 degree. You know that the angle between the displacement and the frictional force, which is this one here. So we come here and we substitute what we have. The frictional force is 100. So this one is 100. We don't have the displacement, and we have cosine of 180 degree. So this is the work done by the frictional force. We cannot go further because we have two unknown. We have this one and we have that. We go into the work done by the weight here, which could be the tricky one. I'm going to leave the link of last video, which can help you to calculate the work done on weight when the object is moving on the inclined plane. So the work done by weight is going to be equal to weight multiplied by displacement. Remember, we're looking for displacement. We don't have it. Cosine of theta. Now let's go to the theta here. If you remember last video, I told you that this angle here, this one I'm marking blue here, this angle corresponds to the inclination. So that angle there is going to be the same as 25 degree. So how do we calculate the angle with the frictional, with the weight? The angle we are looking, the theta we are looking, is this one here. This one is theta. How do we calculate that theta there? That is going to be equal to 90 minus the 25. It's quite simple. Last time, I'm going to leave the link, but last time I explained exactly how to do this one. So we are going for a 90 minus 25 to solve this question here for the angle. So now here we say that this one is equal to mg displacement cosine of 65 degree, which is 90 minus 25. And if you substitute here, We can now substitute everything in the main equation to calculate the network. Remember, the work done by normal is 0, so I'm not going to substitute, and the initial speed is 0, so all that is 0. So when we substitute, all we have is 100 displacement cos of 100 degree plus 294 multiplied by displacement cos of 65 equal to half mesh, we can substitute the mesh, which is 30, and this is it, the final velocity speed. We have it as well, which is 2 square. And this, guys, is the end. The rest is just doing calculation. The rest is doing some calculation. We're going to question 3 just now, but let's substitute here everything we have. Let's finish this one. After doing all the calculation, you will get that the displacement is equal to 2,47 meters, and this is the answer for this question using the work energy theorem. It's not that bad, really not that bad. Let's go to question 3 and final question of the video, and it's almost the same, but the object is going to move up and incline. A 6 kilogram block slides down we move with a constant velocity of 2 meters per second on the horizontal surface. It hit a rough surface, causing a constant frictional force of 15 Newton. The frictional force on this area is equal to 15 Newton. The block slides 2 meters under this influence until it moves up the incline, which makes an angle of 30 degrees with the horizontal. The block moves a distance s up the incline. Draw the free body diagram to indicate all the forces acting on the block while moving on the frictionless incline. There is not friction on this side of the equation, so we have to draw the free body diagram for here. But first, as usual, we're going to do the free body diagram on this side. It's quite simple because there is not friction. This is the y-axis, this is the x-axis, and the only forces there are going to be weight straight down. That one is not straight down, it's straight down. This is weight and normal force. There is not friction, guys. This one is normal force. So those are the only 2 forces, and therefore in question 3.1, that is the free body diagram they want. One with the normal force, and then one with the weight pointing straight down. That is the free body diagram they want. Question 3.2, they say show that the speed of the block at the start of the incline is 2,45 meters per second. So we are going to use the work energy theorem. You can use Newton's law, you can use equation of motion, but the purpose of this is to use work, so we are going to do that. The net work is equal to change in kinetic energy. Now, for this part of the work, you do have friction, and if you do the free body diagram, which is in this case this one, you can see that the work done by friction, the angle is 180 degrees. Weight does not do a work here. This one here is normal, this is a n, and the normal force does not do work. So the only force that do work is the frictional force. So in other words, the net work will correspond to the work of the frictional force, and this is equal to the change in kinetic energy. This one is frictional force multiplied by displacement multiplied by the cosine of 180 degrees, and this one is half mesh final speed square minus half mesh initial speed square. And if you substitute all the values here, you substitute and you calculate. I'm not going to do the calculation because it's quite simple. It's just use your calculator to do all this, and you will get that indeed the final speed is going to be 2,45. when they ask you to prove something like this one, it's quite simple because the answer must be that number, and if you don't get that number, you know you're making some kind of mistake. Now question 3.3, determine the distance as the blow will move up the slope, and this one is similar to the previous one, but the object is moving up the slope. You have only two forces acting there. One of them does not do work because you can see here the angle is 90 degrees, and the other one, the angle of with the displacement is this one here. Remember, is going to be 90 plus the angle of inclination. I will leave the link for this video. This one is the angle of inclination, which is 30 degrees, and we are going to apply Newton work energy theorem once more here. So it's exactly the same. 3.3 work net is equal to change in kinetic energy. The only force that does work there is the gravitational force, guys. So then will be the work done by weight equal to change in kinetic energy. And if we substitute the formula, actually here we have that weight multiplied by displacement multiplied by cosine of theta, which is, remember, this number there, and this one is going to be equal to half mass final speed square minus half mass initial speed square. The final speed is 0. Why is the final speed 0 and therefore all that is 0? Because they are telling you in the question here that it stops at that point, it rests at that point. Let's take off these lines of the way. So here is what we have. Now the rest is substitute the numbers. Remember, the weight is mass multiplied by acceleration due to gravity. So let's substitute it here. This is mass multiplied by acceleration due to gravity. Now we can substitute everything here. Something important I want you to notice, this initial speed for the incline is the same as the final speed we proved at the before, because it's the speed with which the object reaches the incline. So guys, this one is the question. Now all you have to do is to do this calculation, and when you do so, the answer for the displacement or distance is going to be 0.61 meters. So this is the question. I hope it helped. This is a very good 3 questions. I hope it helped. I hope you get some clarity on this question. These questions could be quite difficult. If you think it helped, please subscribe for the channel, thumb up, write comments. You can ask questions, and then I'll see you next time. Mr. G here.